So, this is the relation which we derived in the last class, that is for any central orbit we have d2u d theta 2 plus u equal to minus m by L square u square f of u, m being the mass of the object, L being the angular momentum, u is a parameter which is nothing but 1 over r. So, by solving this equation we get u as a function of theta, which is equivalent of saying that we get r as a function of theta, because u and r they are just inversely related to each other. Now, this we have derived in the last class. We solved a couple of problems. We saw how to, if we know the force law, if we know f of u, which is the force law, then we can get a differential equation, and in principle we can solve this differential equation to get the equation of the orbit. And we have seen if we have the differential equation in hand, we can also get the force law, or rather sorry, if we have u as a function of theta, that is equation of orbit in hand, then we can compute d2u d theta 2, put into this equation, and we can get the force law. So, it worked both ways. Now, what we are going to do today is we would try a very specific type of force law and see how does this equation behave. Now, the force we are going to try is the inverse square law of force. Negative sign means attraction. We can also have a positive sign here, but for now let us do it with negative sign. Now, this is a force which is very common to us. We have it in gravitation, and we have similar forces in Coulomb attraction, that is electrostatic. So, gravitation is something that governs our solar system, or actually that governs the universe. So, that way it is a very universal law of force, and the very existence of universe as we know today depends, I mean it depends on this particular force law, right. Anyway, so we would like to see how, if we instead if we use this force law in this particular equation, do we get any special information about the orbit. Now, in order to do that, we first write f u, which will be minus k u square simply. So, what we are going to do is, for inverse square force law, we are going to substitute minus k u square into this equation. Okay, we will just keep it in sight. So, our force law is f of u equal to minus k u square, right. So, if we do that, we immediately see that right hand side becomes u square cancels, this becomes a plus sign. So, m k by L square, which is a constant, right. So, we can rearrange this equation to write d2u d theta 2 or u bar d theta 2, just a minute. U bar is equal to 0. So, we define a new parameter u bar, which is u minus m k by L square, this constant. So, we took this on the left hand side. We defined a new parameter u bar equal to u minus m k square, because it is a constant, the second derivative is not going to vary. So, we can simply write it as d2 u bar d theta 2 plus u equal to 0. Now, this is a very familiar form. Remember simple harmonic oscillation? Under no resistance, under no external force, the simple harmonic oscillation has this familiar form. If you do not recall, I will just remind you, it will be x double dot plus omega square x equal to 0. In this case, just it is equivalent with omega square equal to 1. So, this one will have a solution of the form u bar is equal to a cos theta minus theta 0. As it is a second order differential equation, we need to have two constants in the solution. So, we can either write a cos theta plus b sin theta, or we can simply write u bar is equal to a cos theta minus theta 0. Whole idea is we need to have two unknown coefficients a and theta 0. Right. So, we substitute once again for u bar, which is u minus mk by L square, right, and we once again we take it to the right hand side. So, the left hand side remains as u and right hand side becomes mk by L square, right. Now, if we take mk by L square out of this, then the first term there is a 1 and then there is a L square by mk cos theta minus theta 0, and left hand side is u. Now, what we can do is we can write 1 by r for u, right. So, this equation as we see again can be slightly rearranged. Okay, so I am removing this. I hope you all understand this equation by you all remember it by heart by now. So, let us take it up here once again. So, we can write this equation as L by R equal to 1 plus epsilon cos theta minus theta 0, right, where or actually I can use this place. Okay, so let it be here. Let it be here, where L is equal to nothing but L square by m k and epsilon is equal to a L square or a L square by mk. Okay. So, we see that the solution for this particular law of force in general can be reduced to a form which is given as L by R equal to 1 plus epsilon cos theta minus theta 0, where L and epsilon are two constants which depends on the angular momentum, the force constant k and some arbitrary constant a. So, this equation is a very special class of equation which describes a conic section. So, what is a conic section and how it is special? Conic section is essentially definition of a conic section is we all know cones, right. So, these are 3D structure which is something like it looks like this. So, this is called a cone, a solid object. Now, if we take a plane, let us consider this cone is not solid, it is hollow inside and so basically it has material only along the surface and the inside there is nothing. Now, what do we do is we take a plane and make that plane intercept into this cone. The curve that will be traced out by such interception is called a conic section. Let us look at some examples. I took a picture of it from internet. Now, if that plane is obliquely cutting the cone, then we get a shape which is called a parabola. If the plane cuts the cone with remaining horizontal to the ground, then it traced out a curve called a circle. If the cut is like this, it is an ellipse, and if the cut is like this, it is an hyperbola. Now, why we need two cones especially for hyperbola? Because in hyperbola, if you recall from your coordinate geometry lesson, hyperbola essentially has two components. Okay? So, one component is coming due to the interception with the lower cone, and the other component is coming with the from the interception of the upper cone, which is vertically placed on top of the lower cone. So, we see that depending on the angle at which this plane cuts this two conic system, we have one cone which is placed on the ground and one cone which is put vertically on top of the second cone like this. So, if the plane cuts it like this, then we have a parabola, a circle or an ellipse, hyperbola, depending on the nature of the interception. Now, what is so special about conic section? Okay. Now, we know that the equation which describes here, okay, we do not know, but I am telling you that this set of equation is the general equation of a conic section. Now, how do you define? I mean, is there a mathematical way of definition of conic section? Happen to be there is a definition, which is also a very powerful definition, and this powerful definition. So, I will just erase this bit for a while. I hope that is fine, and we can always get it back. The definition is conic section is the locus of a point P which maintains a fixed ratio of length with respect to a straight line and second a point fixed in space that maintains a fixed ratio. I hope it is readable. Yeah. So, conic section is a point, is the locus of a point P that maintains a fixed ratio of distances from a straight line and a point which is fixed in space. Okay. Now, it is a bit complicated definition. So, let us not go into the writing, we will just try to define it on board, that will be easier, I guess. So, what we need in order to define a conic section is a straight line and a point which is fixed in space. So, let us say this is my straight line and this is my point which are fixed. Now, this point, okay, there happen to be very defined name for this thing. The straight line is called a directrix and the fixed point is called focus. I hope these terms are familiar for you from your coordinate geometry. Now, this is the focus, we call this O, and this is the directrix. We do not have a name for it because it is a straight line. So, this is the locus of the point, let us say, which we are interested in. I mean, I am not intentionally, I am not writing it in a what you call very symmetric manner. Okay, maybe I should actually, maybe I should make it symmetric, otherwise it is difficult to visualize. Right. Now, let us take the location of this point P, which is given by r and theta. So, we are placing our origin at the focus. Okay. So, that is how we get to this type of equation. If we place our origin anywhere arbitrarily, then probably we will have a different form of equation, as also we will see that here we will get theta 0 equal to 0, because as I said, I put it very symmetrically. If theta 0, if the symmetry is broken, then we have a value of theta 0. We will come to that in a moment. Now, what we see is, so what is the definition? Definition is, it has a distance. So, any point on this particular curve maintains a distance d from this directrix and a distance r from this focus, and this ratio is fixed. So, let us call this ratio d by r is equal to epsilon. Okay. So, this epsilon turned out to be this epsilon. We will see that in a moment. Let us call it epsilon for now. So, how do we get to the equation? Okay. Let us call this distance d. So, we get a definition for epsilon. Now, we need a definition for L. Okay. Let us draw a straight line which goes through focus and remains parallel to the directrix. Okay. Let us call this intercept A and this intercept B, right. Okay, I mean, it is not a very symmetric nice drawing, but you get the idea that we are drawing a straight line which is parallel to directrix and goes through the focus, and we are finding out the intercept of this line with these 2 points, right. Now, if this ratio is fixed for all the for all points on this particular curve, then this will be the ratio for of d by OA as well. Is it clear? See, this point P, which has a coordinate of r theta, is moving along, I mean, it can move along this curve. So, if we take this point or that point or any point in between or any point on this side, this ratio of d versus r should always be epsilon. Now, when this point P is at point A, coinciding at point A, then your d is equal to capital D and your r is equal to OA. So, d by r equal to epsilon equal to d by OA. Okay. So, also, okay, that comes later, fine. Now, so it is r cos theta plus d. Now, d is equal to what? D is equal to, okay, this length once again is small d and this length is r cos theta. So, d is equal to r cos theta plus d. Okay. So, and let us call this length OA to be L. Yeah, this L, as you guessed, is the same L. So, r cos theta plus d whole divided by L is equal to epsilon. Now, we start rearranging things. Mistake. Okay. So, sorry. So, the ratio is defined as r by d, not d by r. So, what I defined is inverse of epsilon, 1 over epsilon, not epsilon. So, it will be r by d, which will be once again L by d, right. So, essentially what we have is this d equal to, or epsilon d is equal to L, right. So, if we take d out of here, we immediately see 1 plus r by d cos theta times epsilon d is equal to L, right. Oh, sorry, it's not needed. We just have to replace d with r by epsilon, and that will solve the problem. R cos theta equal to d. So, d is with r by epsilon, right. So, if we take epsilon in, so it will be r 1 plus epsilon cos theta to be equal to L, which will give L by r equal to 1 plus epsilon cos theta. Right. So, because we took it symmetrically, we got theta 0 equal to 0 and we got L by r is equal to 1 plus epsilon cos theta. If our picture is slightly tilted with a reference angle theta 0, then instead of theta we have to put theta minus theta 0, right. So, I can also show you that if I take this point somewhere here, there is an alternative definition, or basically if I change the picture slightly from this side, if we look into a mirror image something like this, where this is your focus O and this is your directrix and this is your locus of the point, and you take a point here which is given as r. So, this equation essentially reduces to L by r equal to 1 minus epsilon cos theta. So, what I can conclude from this, okay, I am not showing that to you, but I can tell you that if you try this picture, if you then this will be your d. So, once again you have to define r by d equal to epsilon, and this distance is your d. Okay. So, these are equally valid picture, both of these are equally valid picture. So, with this we got L by r equal to 1 plus epsilon cos theta. If you try this out yourself, okay. So, in that case this will be your theta. As you can immediately see that this theta and that theta is there is a phase difference of 90 degree between them, or rather 180 degree between them. So, you will immediately see that there is a minus sign coming in. So, L by r equal to 1 minus epsilon cos theta is also a valid equation for a conic section, and we will also be using this equation sometime. All depends on how you chose your focus. We will see later on that depending on, so for example, we all know that ellipse is a symmetric shape where there is one focus here and one focus here, right. So, we will see that if we take our origin at this position, then we will get an equation of L by r equal to 1 plus epsilon cos theta, whereas if I can show you that if I take the shift the origin from here to here, we get an equation which has the form that L by r equal to 1 minus epsilon cos theta. So, both of these are a valid form of conic section equation. Now that we know that inverse square law of force gives rise to a conic section, what does it imply? What is the implication, physical implication of that? Physical implication is not very straightforward, I would say. At this point, what we can suggest that any object moving under a gravitational field or an electrostatic attractive or repulsive forces will have one of this following orbit. It can be a circle, it can be an ellipse, it can be a parabola, or it can be a hyperbola. One of these four, right. Now, it so happens that we can actually, depending on the energy of the entire system, energy of the particle which is moving under the action of central orbit, inverse square attractive or repulsive force, we can comment whether this particular object is a circle or a parabola or an ellipse or a hyperbola, but that comes in a slightly later stage. Right now, what we are going to do is we are going to move out of this we keep this equation in mind, but now we are going to switch topic. we will be discussing Kepler's laws. Kepler's laws of planetary motion. Now, this is not a very straightforward discussion, but I can show you some, I can take you through step by step manner. Now, we all know this very famous picture of Sir Isaac Newton sitting under an apple tree and an apple falls on his head, and we have this very notion that immediately after this a miracle happened and he got an idea of gravitation, how the laws of gravitation work and all. But it is not that straightforward. See, like in any branch of science, or we all know what happens in sports, for example. There is a new record only when there was a previous record. A Virat Kohli comes into picture only because there was a Sachin Tendulkar, and Sachin Tendulkar comes into picture because there was a Sunny Gavaskar prior to him. Records were made to be broken. Like that, similar, in a very similar manner in science, what happens, a new theory is developed only when there is a history behind it. Okay? So, it is not like one single day Sir Isaac Newton was sitting under the apple tree without any previous notion of what could be a gravity, what could be the motion of planets, and suddenly an apple fell on his head and he got the spark of inspiration. It is not like that. So, what we are going to do in the next section is we will systematically, I will try to give you a systematic estimate, I mean systematic what you call chronological description of how the fourth law of, very famous fourth law of Newton, I mean Newton's law of gravitation was derived, and what is the history behind that. I can tell you that it has a history of many hundreds of years behind it. It is not one day work. Okay. So, we will in the beginning of next class, I will go take you through a very small presentation on certain very famous names you are familiar with probably, and I will show you how their work was motivated, I mean their work motivated the discovery of gravitational field.